In this video, we will learn about the power rule for integrals. So the power rule for integrals is the following. If you have a function to a certain power n, and inside the integral you have that this is being multiplied by the derivative of the function, then you can use this formula here. That is the function to n plus 1 divided n plus 1 plus our constant. Of course, this is only true if n is not equal to -1. We will cover that case in the next class. So the main components here, you have to detect this function u. You have to detect what is the integer n, or in fact the number n, sorry. And you have to see if the whole situation you can find the derivative of u. So let's see this in a couple of examples. So let's start with this one. So we want to calculate the integral of x plus 3 to the 7th. So in this situation, the power part of the integral is something to the 7. So in fact, we can see that this is our function u that we want to use in our power formula. So the main question is, do we have the derivative of u inside our integral? So let's write this all together. So we have that u of x is x plus 3. So the derivative of u is in fact equal to 1. So we can rewrite our integral as follows. So this is the integral we want to compute, and we can rewrite this as right, because multiplying by 1 changes nothing. So now we have here u, right? This is u of x, and we have the derivative, that is u prime of x. So now that we found what u is, and we saw that we have its derivative, then we can calculate this using the power formula I just gave you. So this will be x plus 3 to the 8 divided 8 plus our constant. So what are we using in this situation is that this is n in our formula and that this is our function u. So this is how we use the power formula. Let's see a more complicated example. So let's see this one. So we want to calculate the integral of the function square root of x squared plus 3 times 2x. So let's try to use the power formula in this case. So as always, as we always do with roots, we can transform it into a power. So what we want to find is this integral, and we can rewrite this as x squared plus 3 to the 1/2 times 2x. So now let's see if we can use the power rule. So we are interested to use this one as the function u of x. So the question is, do we have the derivative of u multiplying outside the power? So we want this to be the derivative of u. And the answer is yes, right? Because if u of x is equal to x squared plus 3, then the derivative of u is equal to 2x. So we can use the power rule in this situation. So the power rule then tells us that the integral we are looking for, it's equal to x squared plus 3 to the 3/2 divided 3/2 plus our constant. We won't always have exactly the derivative of u in our integral. Let's see an example that deals with this situation. So let's try to calculate the integral of the function x cubed times x to the 4 plus 2 to the 5. Okay? So we want to try to use the power rule in this case. So let's see if we can use the power rule with this as our function u of x. So if u of x is x to the 4 plus 2, then the derivative, it's equal to 4 times x cubed. So do we have x cubed, 4x cubed multiplying our power? The answer is no, we only have x cubed. The good thing is that the difference between the actual derivative and what we have is just a constant. If that is the case, and only if that is the case, if the derivative and what we have differs by a constant, then we can try to fix this. How do we do this? As follows. So this is our integral. And the thing is, we want this to be not just x cubed, but we want it to be 4x cubed. So the main trick is to force it to be 4x cubed, but if we multiply by 4, you have to divide by 4 to make this equal. But now we can use properties of the integral to take this 1/4 out. So this will be equal to and now we can use the power rule, because now we have exactly what we need. We have the derivative, and this is our function u of x. So with those two pieces together, we can find that this is 1/4 of x to the 4 plus 2 to the 6 divided by 6, and all that plus our constant.